Very good. So this is lecture 3, and today we are going to discuss things that properties of, basically we are going to discuss properties of space-time. And one thing that you will see compared to the last two lectures is that we'll soon get into issues about space-time which don't really have a counterpart just in ordinary space or in Riemannian geometry. So they'll be very Lorentzian. You might be aware that there are even textbooks, a few, not many, on Lorentzian differential geometry. That means differentiable manifolds with a metric that has a minus plus 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 type of signature. So we'll see that that's going to manifest very soon. But even before that, the object we are going to deal with today and tomorrow, and maybe even next week, part of next week, are geodesics. So let's give a definition. A geodesic is a path whose tangent vector propagates parallel to itself. In principle, I should have defined a path, but you can sort of figure out. So let's just establish some notation for all my lectures. The manifold will be called M, and I'll put it in a rectangle. That's the whole manifold of space-time. We'll also give rigorous definitions, but later, because if we start trying to be very rigorous now, we'll get bogged down in a lot of details. So I wanted to be rigorous only a little bit later. Fine. So this is a manifold, and it's always d-dimensional. And as I told you last time, its signature is like this. And a path is basically a one parameter family. Okay, now you can discuss this path in Riemannian geometry or in Lorentzian geometry. They are similar in some ways and different in some ways. What I will do here, I think, is to start directly with the Lorentzian case, but the notes have a little bit of preliminary with the Riemannian case. So what we'll do is, the path will be described as x mu of lambda, and lambda is the parameter that labels the point on the path, and x mu will tell you the space-time point corresponding to that lambda. Okay, so the tangent vector, by definition, to such a path at any point is v mu is equal to d x mu by d lambda. Okay. Now what's the condition that it propagates parallel to itself? Well, let's take v nu. If we propagate it a small distance, it means we are differentiating it. Differentiation is always done by the covariant derivative del mu, but it should be the directional derivative which is along that same path. So I should dot it by this. So v mu del mu v nu is the infinitesimal parallel transport of v nu parallel to itself, and the statement that this is the infinitesimal transport along the path, and the statement that the transport is happening parallel to itself is that this should be again proportional to v nu, with a function here which we'll just allow for now to be arbitrary, called j of lambda, which can vary along the geodesic. Now you would guess immediately seeing this equation that if there is really a j, then although the vector is always propagated parallel to itself as per the geometry of this manifold, it may change its length. And that's in general what happens. Okay. Now we'll see how to do better in a minute. Let's also write this equation a little bit more explicitly. So this thing we can write as gradient with respect to lambda, the direction along V, and since this is dx nu by d lambda, so gradient lambda of this by definition is d2x nu by d lambda squared plus an affine connection term so that's the expansion of the left side of this. On the right side we have j of lambda times dx nu by d lambda. So that's the requirement of being a geodesic. Okay. Now it's well known that in Riemannian manifolds a geodesic minimizes the distance between 2 points, and here it's a little bit more subtle. So first let's recall what is the distance. So the invariant distance in general relativity for 2 points that are very close to each other is g mu nu of x dx mu dx nu. So that's only the invariant distance between 2 points that differ infinitesimally. To find out what is the distance for points that are at a finite separation, we need to integrate this thing and finite distance. Then we get a number which we can call, probably misleading, but I'll call it L for now. It's just the integral d lambda root of g mu nu x mu by d lambda and this will go from lambda 1 to lambda 2. Now if this was all Riemannian, it's easy to show that the geodesic defined by this parallel transport will minimize the distance, and so in the Riemannian case it minimizes the distance. But it's amusing to remind ourselves that there is no way to maximize the distance in a Riemannian manifold, because I have a manifold, I have the starting point and the end point, and my curve can just keep wandering back and forth between them as many times as you like, or it can just go for a tour around the whole manifold as many times as it wants. So there's no maximum distance. It's not bounded above at all, this length. Curve can go everywhere, can travel. It's a very simple, trivial fact, but it's worth noting. On the other hand, in a Lorentzian manifold, we have an interesting situation. First of all, that quantity ds squared can be less than 0, which we call time-like, or it can be greater than 0, which we call space-like, or it can be equal to 0, which we call null. Now these are all statements at a particular point. If I'm at some point, my distance between that and a neighboring point, depending on the direction where the neighboring point sits, can be any of these 3. Okay. Now, for a general curve, of course, a general curve does not have to be time-like or space-like or null throughout. It can change. You can, so here for now, from now on, we need to have this important aid to our understanding. The space coordinates are all represented by horizontal coordinates, and time is always vertical, and we always look at space-time diagrams. Okay. Yeah, good. So now, if I'm at this point, usually I draw this diagram and the origin is the point I want to discuss. Then I simply draw the light cone, and now if my vector is here, then it is time-like, which I'll abbreviate by TL, I'll draw it with a double arrow to show that it's not a coordinate axis, it's my chosen vector. And this one is space-like, and then this one is null. And then as I travel, it can vary. However, there's a very important theorem which actually ensures that for a geodesic, if it's time-like somewhere, it's time-like everywhere. Likewise space-like, likewise null. And let's prove that theorem. It's just a little bit tedious. So the statement is, okay, so before we prove that theorem, we have another theorem. The function j of lambda can be set to 0 by a suitable reparametrization So lambda prime is my new parameter, and I'll just define lambda as a function of the new lambda prime, and I'll show that there is always a lambda prime such that j of lambda in lambda prime basis is 0. As a result, in terms of lambda prime, the equation of the geodesic is that the covariant derivative along it is 0 rather than being j times itself. So let's prove that theorem. Of course, this should be invertible, otherwise I won't know what sense to make of this. Good. So let's do the following. Let's define some simplified notation that dx mu by d lambda, we'll just call it d sub lambda of x mu, just to shorten our formulae. Now, that change of variables, we have that d lambda, I can write it here, is the same as d lambda prime by d lambda prime x mu, just chain rule, okay, and then therefore the directional derivative along the geodesic of d lambda x mu, which is the left side of the geodesic equation, in the new parametrization, it's d lambda prime by d lambda whole square times this plus d2 lambda prime by d lambda squared d lambda prime of x. And it's easy to see why this is so. So we have this formula, and now what we want to do is to require that this should be 0. That means when this is set to the geodesic, the right hand side of the geodesic equation, j times d lambda x, then this should be 0. So that puts a condition, and the condition is that, there's a bug in my notes, slight notational thing. So this one, remember, to start with was j lambda d lambda x. So the requirement that this be 0 if this is equal to j times dx mu means that I should choose lambda prime such that this is exactly equal to that. Good. And that means that j of lambda is equal to okay, so it's a easy, it's done in the notes, but let me just write the answer. It's d by d lambda log of d lambda prime by d lambda. I skipped a step. It's just repeated application of the chain rule. So from this, we get, where did my eraser go? From this we get d lambda prime by d lambda is equal to exponential of the indefinite integral up to lambda of j, will give some dummy variable j of sigma d sigma. It's just a one, j just depends on one real parameter, so it's easy to integrate. So I find this, and one more integration gives me lambda prime. Of lambda, which is what I want. So it's possible. All I wanted to show is that it's possible. I think this is very elementary and people know all this, but it's important to set the stage for a few interesting things that will happen. So I'm just going through it as quickly as possible. So now, henceforth, we'll assume that this process has been always done, unless specifically we say otherwise. So therefore, all our geodesics will satisfy V mu gradient mu V nu equals 0. This will be our equation for any geodesic that we'll consider. And in this case, lambda is called an affine parameter. And the geodesic is said to be affinely parametrized. Okay. Now, of course, this is all in principle, so it's not obvious that every time you can integrate that j very easily. I mean, it's doable, but it might be tedious. But there's a very nice case. So this much is true for all types of geodesics. But there's a very nice way to do it if the geodesic is time-like. But before that, let me notice, one second, that, good. So I should point out here that the norm, so once this is true, once it's affinely parametrized, I've gone back to calling it lambda now. I don't want to keep calling it lambda prime. But once it's affinely parametrized, we have a very nice result, which is that the norm of the vector now remains unchanged as we parallel transport. It's pretty obvious because what's happening is this is the amount it changes and that's 0. So it's really the same norm as it was always. Yeah.
The frame in which this lambda prime is there, is it special in the sense that we are choosing that frame where something related to proper time?
Yeah, not yet. I'm about to say that. But first of all, there is no such thing as proper time in the null case or the space-like case. So that's special for time-like. That's what I was about to say. But I just want to make the comment that it's not a frame, it's a parametrization, the choice of the parameter lambda. And we'll also see in a moment that that choice remains affine if we make a linear transformation. So two things. One, norm of V remains unchanged in the affine parameters. Affine parameterization as we go along the geodesic. And this leads to a very important consequence, which is that the property of being time-like, space-like or null is no longer true only at one point. If it's on a geodesic, then the geodesic which is time-like at one point has to be time-like forever because of this statement. Okay? So, every geodesic, this very important result is completely time-like, space-like, null along its path. So there's no possibility that it can change between these. Now some physics which I'm sure you know. A time-like geodesic is the trajectory of a free particle, free massive particle, and a null geodesic is the trajectory of a free massless particle. And a space-like geodesic is not the trajectory of any particle, so we can stop talking about it right now, and we won't really come back to them except once in a while to just mention something. Okay, so this is one fact. And then the second fact is that for the time-like case, tau, which is the proper time, so which is square root of is an affine parameter. How do we prove this? It's just a one-line proof. We have this equation can equivalently be written as g mu nu dx mu by d tau dx mu.
dx mu d lambda.
No, now it's tau. We are choosing tau to be lambda, or we are choosing lambda to be tau.
I see. No,
Sorry?
inside of the square root d.
So this is d tau. Sorry, yeah. So this equation is the same as saying this is -1, and we are basically done because this is nothing but the norm of the tangent vector and it's constant, so it has to be affinely parameterized. Okay, but you can't do this for the null case. For the null case, the norm is 0 and the norm is 0 whether the geodesic, the tangent vector has norm 0 in a null geodesic, whether or not it's affinely parameterized. Okay, so you can still make it affinely parameterized by the method I gave, but you can't use the property of the norm. The norm is just 0, and this is one of the most confusing things about null vectors, and there are many more which will come now. Okay.
So why are we calling this free massive particle, free massless particle?
I'm not calling it, that's what it is. A particle which is acted Newton's law, but in a space-time, in a non-trivial space-time.
Even
Plus
if,
Einstein.
Even if we are talking it without a dynamics, right?
If you put a particle in a space-time, it will follow, and if it is massive, it will follow a time-like geodesic. This is the statement that in Minkowski space-time, a particle follows a straight line in the space-time diagram. We don't have to say what space-time, what line it is. Let's look at an example. So let's just look in 1 plus 1d, which is always the easiest. So what does a free massive particle at rest do? It starts here at t equals 0 and it follows this line. That's a time-like geodesic in Minkowski. Okay. If I give it a little velocity, then it will keep traveling at constant velocity. That's Newton's law, and therefore it will follow this line. If I give it a little more velocity, it will follow this line. Okay. Now Einstein comes in to tell us that I can't keep giving it more velocity, because when I give it more energy, it doesn't actually gain more velocity. That is special relativity, which is valid in this Minkowski example. And so this line can never tip onto this light cone or beyond. And that's that. That's my first statement. The second statement is that if I have a massless particle like a photon, it can't be at rest. So this line is impossible, this line is impossible, this line is impossible. there are two trajectories which are possible in 1 plus 1D. One of them is this way and the other one is that way. Both are null geodesics.
Yeah, I understand that, but I don't understand why it's called free.
Free means no external force. If I make my photon travel through a material, it's not going to travel on the light cone, right? I can slow it down in a material. I can do lots of things. Never mind photon. I can take a particle. What's the trajectory of a massive particle which initially is at rest and then I give it an impulse? That's the trajectory. It's not a geodesic. Free means no external force. It means the same thing that it means in Newtonian physics. Just unless acted on by an external force. The same idea.
It's not a geodesic, but it will remain time-like.
But it will remain time-like. Exactly. That's it. Okay. Now there's a little result which I won't spend time on. It's very easy to derive. Comes from the fact that the geodesic equation is second derivative. The leading term is second derivative of x. So lambda going to a lambda plus b preserves affine parametrization. So if lambda was an affine parameter, then the new one a lambda plus b, where a and b are constants, is also an affine parameter. And that's the only freedom I have. If I make any other transformation on lambda which is not constant, shift or linear, it will spoil the affine parameterization. So this is the complete freedom we have. Okay, good. Now, good. So this is a bunch of things I wanted to say. Now I'm sorry, I'm really, I tend to lose my memory from time to time. So did I discuss isometries yet? Yes, very good. We wrote Killing's equation, right?
Yes.
Good. So now what we can do is ask about the relation between isometries and geodesics. Of course, they are strictly not related because geodesics always exist and isometries may not be there. Very, very important to realize that there can be manifolds with no isometries, neither continuous nor discrete. There can be manifolds with only discrete isometries. There can be manifolds with continuous isometries. I think we derived also an upper bound last time on the number of continuous isometries. Okay. However, if there is an isometry, then there is an interplay between that and the affinely parameterized geodesics, which is very nice. So suppose M does have an isometry. Okay, sometimes I'll forget to say continuous, but if I give you the vector field for the isometry, obviously it's a continuous isometry. So this is the vector field which satisfies, just to remind ourselves, this plus this equals 0. Then W dot V is constant along any affinely parameterized geodesic with tangent vector V. It's a very simple but useful result. Let's prove it quickly. It's very easy to prove also. So when I say something is constant along a geodesic, I mean that V mu, gradient mu of V, let's say nu, W nu is 0. So we have to prove this. For that we expand this covariant derivative. One term comes where this acts on this. This vanishes by the affinely parameterized geodesic equation. And there's another term where we have V mu V nu, gradient mu of W nu. But by the killing equation for isometries, this is antisymmetric in mu and nu, but this is symmetric in mu and nu. So this is also 0. So we proved our little theorem. Good. Okay, are there any questions so far? Questions, comments? Very painful, not so painful? It's a recap of what you should know, but it will slowly get, actually rapidly get more complicated. So now we are going to define a congruence. And this is more fun than just one geodesic. And we are going to just introduce a wee bit of topology here. So, the definition. Given M, which is of course a space-time of dimension d as always, and an open subset. Now remember, in terms of manifolds, if I have an open subset, it's an open set in the topological sense, which very crudely you can think of as that it doesn't contain its own boundary. But importantly, it's the same dimension as M. You can't have an open set of a manifold M which is of dimension d minus 1, d minus 2 or anything. It has to be dimension d. So the picture we have in mind is here is M and here is O. And somehow, okay, why it's open, these things will kind of become more relevant later on, and we'll really have to use topology for a few things. But today it's not very important. So given this, a geodesic congruence is a family of geodesics such that every point P in this open set lies on precisely one of the family. So if I pick any point P, it's a space-time point, remember. And if we have a congruence, there must be one geodesic and only one which passes through P. But if you pick another P, say P prime, you'll also find another geodesic which passes through P prime. And you can sort of get an intuition that it's like a very closely packed network of parallel lines. I mean, of course, parallel doesn't mean anything in a general manifold, but you can imagine that it's a stack of lines. Each geodesic roughly is like a line. In Minkowski, they really are straight lines. And they never intersect, because otherwise this would be immediately violated. Good. Okay, now actually technically this you can first define a congruence without saying geodesic. Then it's a family of curves which has this property. Then a geodesic congruence is that congruence where all the curves are geodesics. Okay. Now since every geodesic individually is time-like or null or space-like along its entire path, so we can choose the whole congruence to be time-like or null. And that's really the only case that will be of interest. Honestly, at this moment, I'm not sure if it's even possible to do otherwise, but will be chosen. Fully time-like. That means all geodesics in that family are time-like or null. We're not going to discuss space-like congruences anyway.
Sir,
Yes.
W is an isometry.
Yeah.
It produces a vector, a trajectory,
Yeah.
a curve,
Yes.
and W dot V is constant and V dot V is also constant.
W dot V is constant along V.
Along V.
No, V dot V is also constant along
dot
V.
is
Yes.
also constant. So does the curve that W makes is a geodesic? Is the curve?
No. First of all, remember that the W is a vector field, so it's defined everywhere. So let's try to make a picture of. So this is referring to the previous thing. I moved on, but it's good you brought it up. So here is M. Here is a geodesic, and it has a tangent vector V at any point. Okay. W on the other hand is a isometry. So there's a direction. There's a whole vector field of W. V is a vector field only along a one parameter curve. It's a particular geodesic. W is a vector field on the whole manifold. Now we are basically saying V dot V is constant, that is because this is affinely parameterized, and W dot V is constant is the statement that this inner product at any point on the geodesic, the vector W of this vector field which lives everywhere dotted with V is constant. There are two different statements.
Every one of those lines which W makes is not a geodesic.
Of course not, yeah. The only geodesic on this is the one along V, is the one labeled by V. Yeah.
These geodesic congruents are, is it just saying that no two geodesics coincide at a point?
It's not just saying that, it's also saying that, but it's also saying there are no holes, so there's no place where geodesics are failing to pass through. It can't be a congruence if I forget to pack every dot in that manifold, every point in that manifold, or at least in that open set.
There's no hole in your manifold M.
No, that I didn't say. The open set is an open set of the manifold. If there is a hole, you have to go into the discussion whether that open set encloses the hole or doesn't. It can. For example, I would advise to be a bit careful. Imagine I have a manifold with this part missing. Now I have to decide carefully if this boundary is also missing or not missing. Is it in the manifold or is it in the missing part? Can't be in both. Let me put it in the missing part. Then the manifold ends here on this dotted line and you can't get any closer. That's a standard construction. Okay. Now I could have my open set like this. And the open set has two boundaries, the outer boundary which it doesn't contain and the inner boundary which it also doesn't contain, but it's still an open set. Now there are no points here, there are no points of the manifold in there. These points are neither in the manifold nor in O. So I don't have to pack my geodesics into this excluded space. Just to the points where the manifold is, where the open set exists. So in this case, this is M, this is O, and this is, I'll call it H for the whole. And so this is actually O. And in this region, any point in this region will have a unique geodesic passing through it, if I have defined the congruence. Good. Okay.
So like the uniqueness part, so suppose in this example, the geodesic can be extended beyond the open set too, right?
Not necessarily, that's the whole point. So if, for example, I could have, and we'll be talking about this, I could have this situation.
Yeah, that's what I was asking.
Yeah, but it's not in the open set.
Yeah, outside the open set I can intersect.
This means that if I try to extend my open set to go here, I don't have a congruence anymore.
Yeah.
It's a congruence only in the open set.
Yeah.
So it's a congruence with respect to a given open set. It can fail to be outside that. It can, it may not, all depends on details. Good. Okay, now since we have defined congruence, geodesic congruence, and all the vectors in the congruence, all the tangent vectors in that congruence are either time-like for the time-like congruence or null for the null one. So for the time-like congruence, we'll simply always assume that we have taken V dot V equals -1, so specific value. The value of v dot v doesn't change since they're assumed to be affinely parameterized, but the value could have been minus any number, but I'll choose that number to be 1, minus 1, which is a choice of normalization, and obviously if it's minus some other number alpha, then I can just divide by square root of alpha and I can observe that. Okay. But for a null congruence, we have the very frustrating fact that v dot v is 0, and if you scale v however much you like, v dot v just continues to be 0. It's really bizarre, and you can, I think, live a full life and never get out of the puzzlement about this thing. It's just null vectors are very strange things, and a lot of physics in GR comes from the behavior of null vectors, which after all is the behavior of light. And so now the next topic we are going to discuss is an extremely important one, is the topic of a null hypersurface. And it's a digression because I just defined a congruence, so I should give you a lot of properties of congruences. But the properties of congruences depend on whether they are time-like or null congruences. For time-like, I could start right away and give you all the properties. There are some nice equations, but it's nothing that really stretches the brain too much. But for the null case, we have to do some preparation. So therefore, now digression to the topic of null hypersurfaces. And with this, after this digression, we'll come back probably tomorrow and discuss the actual properties of congruences, both time-like and null. Okay. So what's a hypersurface? In M is a T minus 1 dimensional submanifold That's it. That's what a hypersurface is. It's a co-dimension 1 or D minus 1 dimension manifold, submanifold. And given a hypersurface, its normal vector V is defined to satisfy. So this is also a definition. So these are the two things we are defining right now. So a normal vector V satisfies V dot W equals 0 for all W tangent to the hypersurface. Intuition is clear. I have a hypersurface, it has a direction which takes you out, so there should be a vector which is orthogonal to everything in that hypersurface. And well, if I do it in, this can also be defined in ordinary space, in three-dimensional Euclidean space. Any plane is a hypersurface, and there's always an orthogonal vector to a plane, yes?
This definition will not be true in the null hypersurface.
It is true in the null hypersurface case. Now, continuing this definition, normal vectors defined to satisfy V dot W equals 0 for all V W tangent to the hypersurface, and still part of the same definition, a null hypersurface is one for which V is null. And this is what was just pointed out, that this violates our intuition, because the normal, V is the normal, but if V is null, then any W so any W, V is supposed to be orthogonal to any W in the hypersurface. Therefore, V itself is in the hypersurface. So it's normal to the hypersurface while also being tangent to it. Is both normal and tangent. I should have given this hypersurface a name. I usually like hypersurface sigma. The null hypersurface I'll give you. Okay. A null hypersurface usually in the literature it's denoted by curly n, so we'll call it curly n. Okay. Okay, was that clear? Now there are some obvious examples. Okay, so the first thing that might be puzzling is, let's consider this null hypersurface. V is one of its internal tangent vectors. So there must be d minus 2 more of them because it's d minus 1 dimensional. So there's one more vector missing. Where is that vector? What is it doing? So that vector is neither, there should be, or by linear independence, there must be another vector not necessarily unique, that is neither normal nor tangent. And there are some simple examples given in the notes, but let's just look at the case again of 1 plus 1d. So in 1 plus 1d, these are the trajectories of a photon. Let's again think clearly what trajectories they are. This is a photon whose initial direction of, see, this is 1 plus 1 dimension, so there's only one space direction. So the photon has to go along the x-axis. Its only choices in life are whether it goes towards increasing x or negative x. If it goes towards increasing x this, if it goes towards decreasing x, then it's that. Now as per my definition, both of these are null hypersurfaces. Each of these separately is a different null hypersurface, so I can call this n. Okay. Now there are only two linearly independent vectors in this spacetime because it's a 2D spacetime. So the vector pointing this way I will call v, is the vector which translates x and t by equal amount, and the vector pointing this way I will call u. And now you can see that v both lies along this n, and it's the normal by definition that v dot anything in n is 0. U on the other hand, if in a picture it's going out, so I might have thought it's normal, looks normal, right? But actually, it's not orthogonal to v, which is the direction of n. And in fact, according to this, I'll find that u dot v is not equal to 0. You can easily make an example and verify that. Actually, we'll do it right now. In coordinates, if this is Minkowski space, let's take v to be 1, 1. This is t, this is x. And u to be 1, minus 1. By taking the component along t to be positive, I made sure these are future directed. That is also something that we'll discuss in more rigorous detail later. But you can see that there's obviously a past directed vectors, but future and past for this discussion is trivial because this is the same space-time direction. What is remarkable is that these two are not the same space-time direction, but they are the same space direction. This is just a particle moving along x and this along minus x. They're the same spatial direction. And this is why space-time diagrams are so baffling. They're not the same space-time direction. Now you can easily see that with the Minkowski metric u dot v, okay, we can, since they are null, I can normalize them by anything I like. It's convenient to put 1 by root 2, and then I immediately find that u dot v is minus 1, which is a standard choice of inner product. Okay, so that was for a that was for Minkowski. Yes.
If we consider a time-like geodesic,
Yeah.
its norm is less than 0.
Yes.
But if it intersects itself orthogonally, its norm will be 0.
Sorry, wait, what time-like geodesic?
And if we have a time-like geodesic,
That.
yeah, if it comes back and intersects itself orthogonally, it's v dot v will be 0, but v dot v should be constant.
No. First of all, this is all these are all space-time diagrams. So just because something hypothetically does this, that doesn't mean that v dot v is 0, right? Even this and this have 90 degrees angle between them, but u dot v is not 0. That's the whole point of Minkowski metric. This is the point I've been trying to emphasize. Apart from which, we will make sure that all future directed vectors remain future directed. But anyway, your example doesn't work, because in 1 plus 1D, the only vector that is perpendicular to a null vector is that vector. There is no other vector normal to it.
Can it or can it not intersect itself?
So in physics we don't allow it to, but you keep using the word orthogonally, and do you mean this? But this is not orthogonal. This is what I've been trying to say. You keep using that word.
Okay.
Are you saying that you and we are orthogonal because this angle is 90 degrees, yes or no? This is why I emphasize that it's confusing. It is confusing, and you're not wrong to be confused, but I'm saying you need to appreciate the point I've been emphasizing. This calculation shows that u dot v is not 0. Now look, if this were two vectors in Euclidean signature space, then the dot product of these is 0, because 1 minus 1. But it's not a dot product in Euclidean space, it's a dot product in Minkowski space. Because of that, I have to take minus u0 v0 plus u1 v1. Each of those gives me minus 1, then this 1 by 2, and so finally I get minus 1. That's the whole point. Yeah? Good. Thanks for bringing that up.
Sir?
Yes?
So, U will be unique. Can you say that?
No, actually in general it's not. In this example it is, because we are only in 1 plus 1D.
Because I'm thinking that because there's only one dimension left.
Yeah, in this example it's unique.
In any case, like the hypersurface is 4-dimension 1.
Yeah.
So the vector field that we construct, which is
I'll do that example now. Let's move on from this very simple example to a general manifold. Let's move on to a general manifold, then you'll see how it works. Okay. Sorry, yes.
So this null hypersurface definition is saying that the hypersurface is null if every normal vector is null.
There's not every normal vector. There's only one vector which is normal to all the vectors in the hypersurface, because the hypersurface is d minus 1 dimensional by definition. So there are not many normal vectors. There's just one, and that one is null.
In this case, that is itself.
Okay, sorry, I take that back. So, okay, can I finish the general example? Then I think, not general example, the general theory. I've just given one example and it's too trivial, so it might make things very confusing. Let's do the general example, then you raise your question again. Okay, so now we can't construct vectors, we don't have necessarily some nice coordinate system to work with and all that. We'll simply define our null hypersurface as follows, and then write some theorems about it. So, general M. Okay. Now, we can start with the normal vector. So take a null vector v. So v dot v is given to be 0, and find all vectors orthogonal to it. And then we can try to construct the submanifold such that these vectors make its tangent space. Okay, and what will those vectors be? We can think that, okay, so these are the vectors which satisfy w dot v equals 0. Okay, and then w, so all solutions of w dot v equals 0 are tangent vectors to the hypersurface. You agree with that, right? this is how I am defining my hypersurface. Now, how many such tangent vectors should there be? See, linear dependence has not changed just because we are in Lorentzian signature. Linear dependence is linear dependence. So in a the manifold being d-dimensional, that is a meaningful statement. And we have one vector v which is chosen to be null and to be our normal. Therefore, there have to be d minus 1 vectors normal to it. The new thing is those d minus 1 don't all have to be distinct from v itself. One of them in fact is v. So all solutions of this include v and some other bunch of vectors which I can call x1, x2, x d minus 2. I have to have this, right? And I'm not saying anything about these x's, whether they are null or not null. In general, in fact, they will be space-like. Intuition tells us that. If you do it in Minkowski, they would be space-like. Otherwise, how am I going to span all the space directions of my manifold? It has d minus 1 space directions. So v and all these are the tangent space, generate the tangent space. To my null hypersurface. Okay, good. Now let's try doing it the other way. Supposing somebody did not give me a vector v such that v dot v is 0, let me try to define some hypersurface which has a null vector orthogonal to it. So one standard way is to take a general choice of coordinates, a generic choice of coordinates x mu, and impose that there is one function of all these x mu which vanishes. This is called an algebraic variety. Okay, but it's something very familiar from school. When we define a sphere, it is x squared plus y squared plus z squared equals 1. So that is the function f of x1, x2, x3. And of course, the sphere we get is one lower dimension than the three-dimensional space. So this is a standard way to define a co-dimension 1 submanifold. Now the interesting thing is that since v mu lies on, by the way, I haven't brought in geodesics yet. Okay. Okay, let me skip this thing and go on to geodesics right away. So good. So we have v and these d minus 2. So there's one missing vector. Now the question, one second, is whether that missing vector is null or need not be null. This question was asked a few minutes ago. Yeah, what's your question?
So when we are given this vector v and we're supposed to find all tangents to it,
all vectors normal to it.
All vectors such that w dot v equals 0.
Yes. So a basis for those all vectors will include v itself because clearly it satisfies that equation, and then there will be there have to be d minus 2 more of them.
No, but so v is defined on the entire manifold.
Yeah.
But the normal hypersurface is one dimensionless.
Yes.
So v was supposed to be defined only there, and we are supposed to look at.
Yeah. Okay, that's fine. Actually, you only need v over there. That's correct. There, it doesn't matter, right? You have more information, but we only need the part.
Which what we mean by solving for all w such that w dot v, that won't give us a surface. Is what it is.
Okay, certainly once you have coordinate system, you can actually do it, right? Let me show you how it's done in a minute. Then you can again ask your question. Okay, good. Now, now there must be, this is very important, there must be, this is the d-dimensional case, another vector u which is linearly independent of my had given v and x. I think I should have called this x1, sorry. It is x1, x2, yes. So x a, let's say, mu. Because these are d minus 1 in number, so there must be one more. And the question is u null? And the answer is that it doesn't have to be. Okay, but it can be made null. And the intuition is, if I take u and shift it by an amount proportional to v, then it will fail to be null. Because u plus alpha v, if I take dot product with itself, u dot u is 0, v dot v is 0, but u dot v isn't 0, so it will fail to be null. So the statement is that if u is not null, I can make it null. I can shift it by an amount proportional to v to make it null. So my claim is it can always be made null. So if u is null, we are done. If u is not null, define a new u, which we'll call u prime, and then obviously later we'll drop the prime. And we'll define it by taking u and then shifting it by an amount proportional to the vector v, and the coefficient will be chosen to be u dot u upon twice u dot v. We are assuming u is not already null. Now it's an easy exercise to see that u prime is null, because this gives me u dot u. Square of this gives me 0 because v is null from the beginning, and the cross term is minus 2 u dot v, which cancels this and leaves u dot u, so that cancels the norm of this, so this is null. So we get our important conclusion that we can always think of a manifold as having two null directions linearly independent of each other, where their dot product between them is not 0, but their dot product with themselves is 0. Exactly the opposite of what normal vectors do. Normal vectors have a dot, normal I mean usual vectors, have a dot product with themselves which is non-zero, but if there's another vector linearly independent, we can choose the dot product to be 0. It's exactly opposite of that. Yes.
So what is confusing me here is that this v mu is null, right?
Yes.
So essentially this statement is that if you have some non-null vector and if you add some null vector to it,
Yes.
it will become null.
Yes.
Isn't that confusing?
Extra 2ab. You square this. This doesn't contribute anything when you square it because v is null, what you said. But u dot v is not 0. It's the cross term which does it. This is the whole point about this null geometry. Similar things to the time-like vectors, but everything is a little bit upside down. And we need to spend a lot of time thinking about it because it's extremely confusing. But I'm glad you brought it up. This is the point. It's null, and yet it made this guy null by adding it. But you see the calculation, right? It's the cross term.
Yeah.
Okay, good. Now, a very interesting theorem. I'm just a little tired today, so I might not prove it just now. I think I'll prove it tomorrow. But let me write the theorem and stop. A little early today. Notice that I haven't said anything about geodesics for a while. We've just been talking of vectors which are null and null hypersurface. Where were the geodesics? We forgot about geodesics in this digression. But the theorem says the integral curves, I'll explain all the terms. This is a standard one, of the normal are automatically geodesics. So they are null geodesics. Okay, and therefore they define a null geodesic congruence. So just by having a normal which is null and a null hypersurface, I have a null geodesic congruence whose geodesics run along that hypersurface. So in fact the statement is that the hypersurface is ruled by these geodesics, and this congruence is called hypersurface orthogonal. This is a term that you will find in Hawking and Ellis and in Rial's notes and lots of places. Walled, so hypersurface orthogonal. The picture, I'll draw it like this just to emphasize the null nature of this hypersurface. And you have your geodesic congruence such that every tangent vector on every one of these is null. Okay, so the whole congruence is null and it's ruling the hypersurface. And if there are more dimensions, it's also going down. I mean, it's not just in a plane. It's filling the whole bulk of that null hypersurface. So this, of course, is completely different from what you would have expected for a time-like congruence, where instead the picture is much simpler. We just take a fixed time surface and the geodesics in the congruence poke their way through that surface. So for time-like, and we'll discuss both next time, I would instead start with something like t equals 0 in some coordinate system. It might be a little wavy. This might be a general manifold, not a Minkowski. But I can have some coordinate system and I can just, it doesn't matter. Its important thing is that its normal should be time-like. Okay? And then what are the geodesics? They go like this. They actually poke a hole in this hypersurface. But these instead, null case, they rule the hypersurface. That's a big difference. And all the analysis of null and time-like geodesics differs because of this basic fact. So let me, since this might have been very dry mathematics of space-time, so let me at least tell you a couple of things you may already know.
So can you poke this null hypersurface with time-like geodesics?
Can I go along it? No, because
Perpendicular like this.
Yeah, so I think nothing stops me having time-like geodesics, but they are in that case they will be the example of that U which was not null. So I'm just assuming that I have shifted U to make it null. Yeah, what was I saying? Yeah, so what is the physics application? So let's just mention it. Here, the question in time-like geodesic congruence, the physics question is, how do time-like geodesics behave in the far past or future? And the point is, we already said a congruence is defined with respect to an open set, and here implicitly I am saying, let's suppose we produce these geodesics out of the open set where they are a nice congruence. How do they behave? In particular, do they collide and then the congruence fails to be a congruence? And it turns out that this is related to the question of the cosmological singularity, what people call the Big Bang. So what will turn out is that when geodesics fail to make a congruence by producing them far in the past, then it can be that it's a signal of some bad behavior of space-time. This is the question that Amal Raichaudhuri was trying to address, and he did one step in it, but there are two steps. He did one step which was to show that generically, once the geodesics are produced out of their comfort zone of some open set, they will collide and the congruence will somehow go to hell. But you can't always conclude from that the space-time is bad or space-time has a singularity. That extra step was done by Hawking, and that is Hawking's singularity theory. So the Raichaudhuri equation was the starting point to address this question, and it is very deep because he realized, really I think ahead of most of his contemporaries, that studying geodesics is the right way to understand how space-time is behaving. You would think, first I know the space-time and then I'll find out how the geodesics behave, but it inverts the question. It says first I'll look at geodesic congruence and figure out how it behaves. If it misbehaves, maybe space-time is misbehaving, maybe. And his paper was inconclusive. He couldn't go beyond it, and he freely admitted that later. But it was a very, very key first step, and Hawking acknowledged it very prominently in his work. Now, what about the null case? Well, first of all, why time? This is all time-like. Why time-like? Because in the simplest metrics, or in all metrics of cosmology, there has to be a time-like direction, because that's the direction which at any space-time point tells us what is the direction of time. After all, we do experience a direction of time, and there must be something in the metric telling us that. So the geodesics relevant for cosmological singularity are time-like geodesics. Because you could imagine it's like the universe is a collection of mass. So mass, of course, being massive, follows time. Each individual particle will follow time like geodesics. And we are trying to ask whether this mass collapses backwards in time and forms some kind of crunchy thing called a singularity. So time-like are the correct geodesics to embed into this problem. What about null? Well, for null, it's a completely different problem, and is the problem of the black hole horizon. So in particular, the horizon of a Schwarzschild black hole is a null hypersurface, exactly in the way I have defined, and it's a very non-trivial one. I haven't defined any non-trivial null hypersurface, so I'm not giving you any example, but that's the example. So as soon as we get to those black holes, we'll see what the null surface looks like. Now, it's a little confusing because horizon is used for two things. Horizon can be used for a d-2 dimensional boundary of the black hole. That's the thing whose area we measure, right? So in 4 dimensions, there's one is time, 3 is space, and the black hole is a concentration of matter inside a spherical surface. That's not a null hypersurface, it's a space-like surface. It's actual boundary, or it's the horizon such that when you go through it, some things happen and so on. But if you consider a black hole which is forming, then by a collapse, then you find that the horizon is actually a null hypersurface, and its nullness as a hypersurface is the thing which causes the meaning of space and time to break down. So you all know that outside the black hole I have a space and a time. When I'm inside, the radial direction and the time direction get somehow switched or seem to be, and all that has to do with the fact that that horizon is a 3-dimensional null hypersurface. It's also a 2-dimensional sphere. So when we calculate area of a black hole to get its entropy, we are talking of the area of that sphere. But when we want to understand the behavior of that causality near the horizon, then we treat it as a 3-dimensional space-time object which has a null direction sitting inside it and also orthogonal to it, exactly as I've described. So these are some of the motivations. So next time I'll finish this theorem about hypersurface, that theorem, I'll give you the proof that the integral curves of normal to a null hypersurface are actually geodesic. So we'll find that they are null geodesics. And then we'll move on to discuss properties of time-like congruences and then separately properties of null congruences.
So can these two
Yeah.
singularities coincide?
Can?
These two singularities, black hole singularity and big bang singularity.
But there are different questions, right? One is about the behavior of space-time in the far past, and the other is about the behavior of space-time in the center of a black hole. Far past and center of a black hole are not the same. They're different parts of space-time. First of all, in the time-like case, we just have a space. We don't need to have any black holes to discuss it. In this case, we need to have a black hole because only then we have a horizon. And of course, you can have massive particles falling into the black hole, but still the black hole intrinsically has a null hypersurface around it. So somehow the role of light rays is very important, and here we get Penrose's singularity. So this plus Hawking's singularity theorem. And here we have what is very often called null Riemannian equation. It's a term that makes us all happy because he was really a person all of us can admire, but Riemannian himself pointed out several times in his life that he never wrote this equation. He kept saying, I don't know why people credit me with the equation, which I didn't write. This is the equation I wrote. It's the equation for behavior of time-like geodesics, and there's a different equation for behavior of null geodesics. Now, not only Riemannian didn't find it, but a person called Sachs found it. And there are a small number of people in the literature who call it the Sachs equation, but it's usually called null Riemannian equation. Yes?
So that cosmological singularity,
Yeah.
does it have, is it a point where the curvature space-time becomes infinite?
Yeah, but okay, so very good question. That is what most people take away from the newspaper reports of Hawking's singularity theorem, but it's not what Hawking said, and it's also not what he meant. Okay, to be fair, Hawking and Penrose quite happily advertised singularities as being some place where everything becomes curvatures become infinite. The only thing that you can really say is that the space-time becomes geodesically incomplete. And to understand that, we have to understand the topological properties of geodesics, and that's a later chapter in this course, which we'll come to maybe in a month. So now, as many people have pointed out, geodesic incomplete, you can argue all day long whether geodesic incompleteness means there is a curvature singularity. Most people feel that, yeah, it's a reasonable interpretation, but nowhere there's a proof that that is what is happening. Yeah.
So, talking about these geodesics, in what sense do you mean that these time-like geodesics go haywire if you go far in the past?
Oh, thank you. That's very simple. They can intersect. So this is your, we already drew this situation. This is your open set O, where it's a congruence and nobody intersects, right? Because remember, every point in this open set O has to have a unique geodesic passing through it. One second. This point, if they intersect, is a point where there isn't a unique geodesic passing through it, because both this one and this one pass through it. So it's no longer a congruence. Okay? Now, using the fact that they intersect and therefore there's no congruence, you can prove that there are, under certain conditions, and I emphasize these are conditions that Hawking added and which were not in Rietzschel's paper, you can prove that the space-time is geodesically incomplete. That means there's no way you can define, you might say this congruence of mine didn't work, but some smart person will come and define a different congruence, and somehow that one will extend into the past. Indefinitely far in the past. But it's not so. If one congruence, under certain conditions, if one congruence, the geodesics all go bam into each other and intersect each other, then it will be a general feature which will point to a misbehavior of space-time, not of the geodesics. But that step, as I said, was not in Rietzschel's paper at all.
But why it has to bam? Like, did not ever.
Because Raichaudhuri proved that it bams. That is his paper. His paper proves that under very general conditions, any time-like geodesic congruence will go bam either in the future or in the past, depending on your initial conditions on some space-like hypersurface, which you can call time equals 0. So either future or past. I'll explain all that, it will come.
Is there
But,
like physical, is there some physical insight to
it's the attraction due to gravity, but it's not just that. Of course, geodesics are not real things, so it's a bit silly to think that there are these lines in space-time and they get attracted to each other, but fundamentally it's from the attractive nature of gravity. But please, there are many conditions you need to satisfy, positive energy conditions, global hyperbolicity, and lots of other things that before which you can't conclude anything.
But let's say there is no matter to begin with. Let's say there is no matter to begin with. Then also will it go back?
Yeah, so there's something called geodesic expansion. It will come actually tomorrow. So let's discuss it tomorrow.
So for null,
Yeah.
null geodesics, this singularity, it means if the null geodesic pass through the singularity, nothing special will happen for the null.
No, slow down. So this is all about time-like geodesics. Now, here the question is completely different. This is, as I said, this is Penrose's singularity theorem. Didn't I write it? Null Raichaudhuri equation and Penrose singularity theorem. Roughly you can say that this theorem has the same relation to this equation that Hawking theorem has to the original Raichaudhuri equation. He took it further and made a physical conclusion which under certain mathematical assumptions is rigorously true. He did the same, but the system is completely different. In this case, the question is whether ingoing geodesics. So the black hole, as I said, has a spherical surface. So first of all, here is the black hole. There's no counterpart in that picture. That picture is about the whole of space-time. In the black hole, what you might think in a normal, so if I have a normal sphere, okay, then then you'll find that there are geodesics going, null geodesics going in and null geodesics going out. Remember, this is a spatial diagram, so this is the same as what I showed you in the beginning when we talked about null hypersurfaces. Plus x and minus x, here it is going towards decreasing radius and increasing radius. Okay, so this is like if you on a space-time diagram, this will be the v vector and this will be the u vector. Okay, and one of these goes to the center and the other goes away. Okay, but I'm sure you know that as per results in black hole theory of black holes, the whole problem with black holes is that once you're in there, there's no direction pointing out. You can't come out. That's why the black holes are one-way membranes, and that has to do with focusing of null geodesics. They focus in such a way that there's no way to come out. That was Penrose's theorem. So it is a very different system. And if you want one crude way to say it is that while a normal sphere gives you ingoing and outgoing geodesics, the black hole horizon gives you ingoing and ingoing. There are two directions, u and v, but both are ingoing. That's the one-line summary of what's weird about the inside of a black hole. There are always two directions, remember, because you have this is the picture we developed of null hypersurface. There are d-2 space-like directions which are minding their own business and not doing anything. And then there are two directions which are both null and linearly independent of each other with a non-zero inner product. But normally those two directions are one ingoing and one outgoing. I'll do this next time. You'll see in a picture how they are. But in a black hole, that's not so. You find something called a trapped surface, and the behavior is exactly opposite of what you might have expected. Yeah.
Yeah. So these two null directions that you are talking about,
Yeah.
They will be not normal to each other, even inside the black hole.
Yeah. They're two linearly independent. Two null directions are never normal to each other. If two null directions were normal to each other, then you would have to have at least two time-like directions in your metric. But your metric has Lorentzian signature, minus and then plus.
Two independent.
Yeah, linearly independent.
And both of these are like focusing inwards.
Yes. So it's so as you can imagine, the stage for this one, the Hawking singularity theorem, is to consider a space like hypersurface, the geodesics which cut it and going back in time. And so there's only one direction you're going back in, which is time. You can go back or you can go forward, but it's one time-like direction. On the other hand, in this story, you consider a d-2 dimensional space-like surface, and now you have two null directions. This is all we just did. Okay, that's why we did it. So I'm giving you now the context in physics why we did it. You have so the Riemann equation actually has a d-1 in the formula, and the Sachs equation or null Riemann equation has a d-2 in its formula in the same place. So that's the key difference between the null and the time-like case. Okay, see you all tomorrow.